from last time, but just the most important concepts. Yeah. So the things from last time, so recapitulation of what I think would be the most important concepts from last time. The first thing is we learned how to solve linear least squares problem, right? A linear least squares problem is of this form where you say minimize 1/2 the Euclidean norm of some vector eta times minus matrix J times x squared over all x, and we found out that the solution is given by x star being equal to the pseudo-inverse of J applied to the measurement vector eta, yeah? And that in the nice case, the pseudo-inverse was given by this formula, J transpose J to the -1 J transpose. But there was this nasty case where we would have an underdetermined problem, and then we would actually solve a problem which would have here an alpha and some little regularization. And if we shrink this alpha to 0, then we will actually get the more general pseudo-inverse, which we can actually define as being the limit of alpha going to 0 of this term where we have J transpose J plus alpha times the unit matrix to the -1 J transpose. And we have shown that this limit is somehow related to the singular value decomposition, which was actually given by Vs plus U transpose, where J is U S V transpose V S V D. So these would be different ways of how to compute the pseudo-inverse and how to give it interpretation. The interpretation is, I think, best captured in this form, where we say it's actually the limit of the solution of this optimization problem when you let alpha go to 0. That means you don't perturb the original objective, but if there's a remaining freedom left, you make sure that then the norm is minimized. And that's all what is happening in this pseudo-inverse. And maybe this formula I should put in brackets because it's not as general, it's only applicable if this is invertible, while this formula is always applicable, and this one as well. So whatever matrix you have, you can define a pseudo-inverse. That was the first thing I want to recall. The other thing is that least squares can be statistically derived, and usually these problems come from a maximum likelihood estimate using assuming Gaussian noise. I will not repeat this, and it's also something that's not at the core of this course, but I wanted you to have heard about it. So when people formulate least squares fitting problems, and they want to use them to estimate some parameters, then there is a statistical derivation for it based on maximum likelihood estimation, but assuming that the measurement errors would be Gaussian, which is a strong assumption, of course. We derived also, or we noted, and that's what we want to do in the next sheet, that there could be also a different estimation problem where you say, I want to minimize the sum of the absolute deviations. So I take here the ith column and then the absolute value, and I sum this from 1 to m, and I don't square it. If I square it, then I'm back at the original one, but if I don't square, then I have what I call L1 estimation. And the interesting thing is, if you want to have this L1 estimation derived statistically, then it can also be interpreted as a maximum likelihood estimate, but using a so-called Laplace distribution. And a Laplace distribution is, this is a Gaussian, this is a Laplace, and one property of the Laplace is that it has more weight in the tails. So it actually assumes more probability for outliers, and that means that it can actually better fit data which contain outliers. And this is the exercise that we will do. So in our MATLAB exercise this week, the first thing is to do something theoretical that's related to this formula. But the second thing that we want to do this week is actually to compare least squares, which is sometimes also called L2 estimation, with L1 estimation. And you will see by constructing some measurement data and some outliers that this L1 is surprisingly stable against these outliers, which is something which is really useful in practice, and that's why it's used. Okay? These are the topics I wanted you to remember from last time. And I see no questions. Yes, there is a question.
Question about the Lagrange function.
Yes.
If the original objective function fx has a domain, not Rn, what's the domain of the Lagrange function?
Sorry, if the original objective is what?
Has a domain.
Has a domain.
Yeah,
Yes.
Rn.
Yes.
So in this case, what's the domain of the Lagrange function?
Actually, you would also restrict the optimization inside the Lagrange function itself will of course only be defined on the domain of its sub-functions, right? I mean, this is a theoretical question which goes back 2 or 3 chapters, I think, but anyway, I try to answer it. So what happens if we have an optimization problem where the problem functions are not defined on the whole Rn, but on some subset, right? And so then, first of all, your Lagrangian function will inherit this restriction, right? So you can only define it there. And if you want to construct the Lagrange dual function, the one where you minimize over all x, you will have to restrict your minimization over all these x's on the domain. And if you are unhappy, then your minimizers will be at the boundary of the domain, and then your problem, this whole thing will break down. But if you're in the middle of the domain with your optimizers, then everything should be fine.
I have this question because there is a logarithm in our Leicester exercise.
In what?
Leicester exercise sheet. There is a problem about the log.
With a log function, exactly, yes. As long.
The x, the decision variable x must be bigger than 0.
Yes.
So in this case, we cannot just use the Lagrange function.
Maybe we should look at that in more detail in the break, and I really look at the formulas and so on. It's already, is it already finished, this sheet, or not?
Yeah.
Yes, so then we can actually discuss it together. Yeah, great. But it's an interesting question. I mean, you can still define a duality and so on, but you will have some restrictions, and we should look at them carefully. Other questions? No. Okay. Yeah, so then what I suggest is that we continue with the next section. And the next section I want to still keep in this chapter of estimation and fitting problems, but it's already an appetizer which will go to the next chapter on Newton type optimization. So if we're looking back at this setting of least squares, and I want to introduce a very powerful method to you, which is called the Gauss-Newton method, or GN. And I introduce it to you even before the Newton method, a bit unusually, because it's coming very natural in this context. So the task that I want to address in this section is actually to minimize a nonlinear least squares function. So where we have something like this, 1 divided by 2, the 2 norm of eta minus a nonlinear model of x. So you see this is now nonlinear, so it is not necessarily a convex optimization problem. It's for sure something that we can aim to minimize, and this function here is of course our objective function f of x in this unconstrained setting that we look at. Okay? And so now the question is, how can we solve this problem numerically? And one idea would be to use our knowledge about solving linear least squares problems and to iteratively linearize this function m. That's a very typical approach that we always do. Nonlinear things are difficult to solve, so let's try to linearize and then use linear algebra techniques that are easy, usually. Yeah? So it's a Newton idea, but in this context it's called the Gauss-Newton method. In order to simplify notation, I will actually call this whole residual before I square it. I will call this thing the 1.5 of big F of x. So that's a big F and a small f, and the big F is just nothing else. And I will probably like to have the big F. I do it like in the script, then it's eta minus m of x. So it's a vector valued function which has all these residuals as outputs, and before I actually square it, I give a name to this function which I call f. So it's very similar to this m, but it's for notational convenience it is easier to use it. And so our optimization problem to be solved is now minimizing 1/2 f, big F of x over x. So this is the problem I want to look at. But it comes from nonlinear fitting. And the idea is to just use linear least squares and to linearize this f, because we know how to solve linear least squares problems. So what the idea of the Gauss-Newton method is iterate x0, x1, and so on. This index should now, these are all variables in Rn, so it doesn't refer to the subcomponents, which sometimes also happens, right? But these are just iterates which all live in the full space. By solving linear least squares. And what is the idea? Based on Taylor series, on linearization. So what the Gauss-Newton method does is actually it chooses some initial point, xk. I call it now xk. So you take a point xk, then you compute the linear expansion of your objective residuals at the point xk. And what we do is actually we solve a problem where you say you minimize, I call it the variable now delta x, which is still in Rn, but I take now a linearization, the first order Taylor series, where I evaluate the f at my point, and then I linearize my f, the big F, the x at xk, and then I multiply this with delta x. So this is the first order Taylor series of my objective function inside this square. And I know how to solve that. That's a good thing. That's why I do it. And then I get out delta x as a function of xk. Right? So by solving the linear least squares. So what will we exactly get here? So let me just continue on the next breakpoint. So what will this method do? It will compute this step delta x, which depends on xk. It will compute it by solving the linear least squares problem. But if you think of this, this is a vector, this f. Yeah, I should put it a bit down, sorry. This is a vector, and this is a Jacobian. Yeah, so I will use a shorthand where I call this thing j of xk. So then I have a Jacobian, and this vector, okay, doesn't have a minus sign like there. That's the only difference, but otherwise I can use exactly the formulas that I had above. And I will use actually the pseudo-inverse if we like that for a moment, and we will get a minus sign because of this. There is no minus sign here, and what we will get is actually j of xk plus times f of xk. So this solution we can explicitly get from linear algebra with the techniques that we had before. And the iteration would then go that we say xk plus 1 should be equal to xk plus delta x, which is a function of xk. Yeah? So we generate a step, a direction in which we should improve our objective by just solving these linear systems iteratively. And then we can see that this is xk minus, and I write now, for a moment I write it this way, xk plus times f of xk, and this would be my iteration. So this is a very simple iteration. I could use the pseudo-inverse, but I could also directly use my formula that holds if the matrix has full rank, and this is actually this J of xk transpose J of xk, the inverse of this whole thing, and then J of xk transpose times F of xk. This last thing is only possible, of course, if the rank of J at xk is equal to n. So if we have enough, if we have really linearly independent columns of this J, then this is possible. So this whole method is based on an iterative solution of a linear least squares problem, and of course we can easily translate it to the original data eta and m if we like. I mean, the J is the derivative of f, and that's up to a sign the same as the derivative of m, and so on. So it's I will not do it because it's just not necessary in this context. But the method is quite intuitive, and at the end it's really something easy. You have xk, you start somewhere, you compute the derivative, you compute some linear algebra operations on the derivative, and that gives you a new direction. Okay. One thing, I mean, this method we will analyze in much more detail very soon, but at the moment I just want to present it as a possible algorithm that is based on some intuitive idea, right, ad hoc. But one thing that we should already find interesting about this algorithm, this will be an iterative algorithm, and if we at any point will be converged, if it would converge, then at some point this xk and the xk plus 1 will be equal. That means that at a converged point, actually this term must be 0. And if you assume that this thing is always invertible, which I will make here, yeah, so then this thing must be 0. Because an invertible matrix times something can only be 0 if this thing is 0. Yeah? So if xk converges to something at x star, yeah, if it does converge, and j at x star times j x star is invertible, which basically means that it keeps the full rank also at the converged point, then we know that j of x star transpose f of x star must be 0, otherwise it could not have converged. Assuming all these, the step is also a continuous function in this x. So, does that make sense? Let's think, does it make sense at all? So why should this thing be 0? And here we can just think of what we did want to solve originally. So what did we want to solve originally? We wanted to find actually the minimum of this function f, right? And the interesting thing is that if you look at f of x, which was 1/2 big F of x squared, and we would compute the gradient of this whole thing, what would be the gradient of this f of x? Don't know if we did that. No, we didn't compute that gradient yet, but it will be the outer derivative, which will be just 2. So this factor here is cancelled, and then times the inner derivative, and what we will get here is actually this expression j of x transpose times f of x. So the derivative of f is exactly given by j transpose t times f. So this is something, if you want, is there a need to do this once really in a detailed form? If more than 3 people want that, I would do it. Is there a desire that I derive this gradient computation in a bit more detail once? Or not? Is it okay? We can just use that formula and you trust me. Okay, good. I'm happy. So the interesting thing is what this actually means is that we have a stationary point of our optimization problem, at least. So good thing is, bottom line, Gauss-Newton can only converge to stationary points. It's not showing that it does converge, but if it converges, it will be to a stationary point. Gn can only converge two stationary points. Okay, so we can look at this equation and we could also say, but this is a bit funny. Couldn't we modify our method a bit to make maybe smaller steps because we want to be more conservative? And this is also at the moment very heuristic. I would just say, why don't we, instead of solving these sub-problems, we could also say we want to penalize the steps a bit so that we don't make so aggressive steps because we don't trust our linearization so much. So we could actually penalize, like we did with the regularization, we could penalize our steps. And then we go to another method which is very related and which is commonly called the Levenberg-Marquardt method, which I also want to introduce you in this sketch form. So it's sometimes called LM. And what this method does, it's the same concept, but it will just say we take an xk, we linearize, and then we say actually the delta x of xk is given by the argument that minimizes over all delta x the objective function that we just had above, namely this thing, evaluated Taylor series. I use now the j times delta x. But we add another term, and this other term is actually a penalization of our step. And so we have here an alpha that might be different in each iteration, which penalizes delta x squared. So this is a bit at the boundary, so you cannot see it, but it's delta x squared. Can you read it? Good. Good. So, and then of course this will give us back xk plus 1, which is equal to xk plus delta x of xk. So this step is then completed. But looking at this, we already know what will be the solution. It will be exactly the solution now with a minus sign, jxk times jxk. This thing, but plus the alpha term, right? Plus alpha k times the unit matrix to the minus 1, and then times j of xk transpose f of xk. So we have a different formula to the step than in the Gauss-Newton method. In the Gauss-Newton method, we had actually this invertible matrix. We had to assume it is invertible, actually, assuming that the rank is n. Here, we have a different matrix where we will always have an alpha k which is chosen to be slightly bigger than 0. And with this alpha k, we will always make sure that this is anyway invertible. It's a very computational attractive thing because then you don't need singular value decomposition and so on. You could actually use this formula always because this matrix will be invertible. And again, we will see that this method can only converge if this term gets to 0, right? Because that is not by definition, but it is by computation, the gradient of our objective function little f. Yeah, so again, the same thing, LM can only converge to stationary points. One other thing we can directly see is actually that because we add something to this matrix and it's inverted, this matrix will actually be bigger in all eigenvalues, in all directions than this matrix, but it's coming with an inverse. It's multiplied with the same thing like here. So we also know that the Levenberg-Marquardt step will be shorter the bigger the alpha is. And so what we know is actually that the step size of a Gauss-Newton will be smaller than a Levenberg-Marquardt. Yeah? And one thing that we could actually even prove is something that I want to only argue here. If you make, so maybe I should first state this thing. So this delta x of the Levenberg-Marquardt method at the same point will be smaller than the delta x of the Gauss-Newton method and the Euclidean norm. Because we have, it's something multiplied with a smaller matrix here. And even more, we can actually show that if alpha k goes to infinity, then this term will completely dominate. So assume that the alpha would get very, very big, then you will have a very big unit matrix here with something small added to it. So you could actually pull out this alpha, and then you see that it's just 1 over alpha, and then there is a unit matrix and dominating this thing, which will be now divided by alpha, so it will be vanishing. And so the only remaining thing is that actually, so the limit of this Levenberg-Marquardt step, which if I regard it as a function of alpha, and I let alpha go to infinity, then it will just be 1 over alpha times the gradient, namely what is remaining here. So it is jx, I directly write the gradient, nabla f of x. So what we also see is that if you add a very big term here, that your Levenberg-Marquardt step will actually point in the direction of, sorry, I have a minus sign here, of the negative gradient. Yeah. So in order to illustrate that a little bit, I just wanted to say that if you would have some optimization landscape in this nonlinear setting, so you could actually illustrate level set lines of your objective function, and here there would be somewhere your minimum, and you are at some point where you, for example here, then your Gauss-Newton method might actually take some assumption. It will compute this step. It's based actually on this linearized model, and this linearized model will actually maybe lead you to some point that might be here. This could be the Gauss-Newton step. Then if you increase alpha, it will get smaller and smaller, the step, and it will be tilted more and more in the direction of the negative gradient, and the negative gradient is actually pointing always orthogonal to the level set lines. And it will make sure that you really go steeply downhill. So as you increase alpha, your steps go from either this Gauss-Newton direction to the Levenberg-Marquardt direction, and the bigger you make the alpha, the more the Levenberg-Marquardt direction becomes similar to the negative gradient. But of course, the steps get also smaller and smaller. So then if you make alpha bigger and bigger and bigger, then this thing will be smaller and smaller and smaller, and at some point you will not make much progress anymore. This Levenberg-Marquardt method, of course, lives very much on having a good adaptation strategy for the alphas, and there are some heuristics around that are part of the implementations of Levenberg-Marquardt method, which I leave out here at this moment. It will turn out that the Levenberg-Marquardt method is very related to what we call trust region methods, which we use for globalization. But these two things were really just to make you a bit hungry. So this, as you see, we have left a lot of questions open. We just derived quite heuristically based on linear least squares on the things that we did here on the last time and which we repeated today. We just say if we have a nonlinear least squares problem, well, maybe we can use these techniques from linear least squares in order to get some algorithm, and then we could implement it and try if it works, and it looks like a heuristic. It is at the moment just a heuristic, but it has this interesting property that it at least would only converge to a point that satisfies first order necessary conditions of optimality. So it's at least not, if it converges, it will at least not stop somewhere at a stupid point, which is definitely not locally optimal, right? So it stops at candidate points at least. But in order to get a better and clearer understanding of these methods, I want to go into the general field of Newton-type optimization methods, and it turns out that both the Gauss-Newton method and the Levenberg-Marquardt method are variants of this general class that we call Newton-type optimization methods. Okay? That is the subject of our next chapter. Chapter 7, Newton-type optimization. And in the statement of the least squares problems, we had introduced this model M, we had introduced this big F, but let's forget about it at the moment again and just say what we want to solve is just an optimization problem with some function f in Rn or in some smaller domain, and I don't care about the special structure of this f, but please keep in mind that this f is very often, for example, a nonlinear least squares objective function. So what we want again is to have some iterates which are called x1, x2 and so on, and what we hope is that they converge to some point x star with some nice properties. That's what we realize, what we would really like. And there is one method that is like the most beautiful of all optimization methods and the fastest converging, in principle the prototype for everything else, and that is the Newton method. The Newton method is what I want to start with, because it comes from other domains. It's useful everywhere, but it's also useful in optimization. And the idea here is that we just look for roots of some nonlinear function, and the root finding problem that we look at is actually the root finding problem where we say we want to find some point where the gradient is 0. Let's just say this is what we want. For convex functions, this would be exactly sufficient even, right? But why is this meaningful? Because the gradient itself has x components. X itself has x components. So it has n components, right? So the nabla f as a function, it's actually a function from Rn to Rn. Because the gradient itself has n components. So it is a square nonlinear system of equations. So we can actually apply Newton's method to it. And I think, I will not introduce new notation here. But what does Newton's idea do? Newton's idea is similar to what we already did here in this Gauss-Newton context, but we do it directly to the gradient of f. And the Newton idea is actually that we again linearize this nonlinear root finding problem at a certain variable and use then a linear system solution in order to get a better guess for the solution. Maybe I should first ask, who has seen the Newton method somewhere before, probably at school or in previous courses? Newton's method. Yeah, everyone? Good. Who has seen the multidimensional Newton's method before? So the one with many components. Not everyone, but most of you. Okay. So we use actually the multidimensional Gauss-Newton method, but it's the multidimensional Newton's method applied to this root finding problem. And the idea is actually linearize. So the Newton idea is linearize and solve linear systems. So two things that we can do. We know how to linearize things, we know how to solve linear systems. What we don't know so easily how to solve nonlinear root finding problems. And so how do we linearize that? So again, we need to think of what is the input for each step. Actually, we start with a current iterate xk. That's our linearization point, and at this point we make a Taylor series which just says we evaluate the gradient at this point. It's probably not 0 yet, but we make a model which is based on the next derivative of this function, which turns out to be, of course, the Hessian matrix of f times the step that we want to make. And let me note the step delta x. Yeah? And we require this thing to be 0. And then by solving that system, we get a next iterate. And of course, we assume again that we can invert this matrix. Invertible. And if we do that, then we can actually get delta x of xk is being equal to minus nabla square f of xk to the minus 1 nabla f xk. And of course the iteration will be then that we add this delta x to the old value. So what we do is actually xk plus 1 is equal to the old xk plus the step, which will be this iteration. So this is called the exact Newton's method for optimization. Exact Newton for optimization. We will later cover in a theorem the general convergence theory of Newton type methods, but it will be locally quadratic convergence. So that's a general property of Newton's method, and it will be inherited here. Oh, I just realized that in the script I very often use delta x p. So I just wanted to make this connection delta x, I will very often also just call p in the script. So whenever I think of a direction in the space of optimization variables, I call it sometimes p and not delta x. But the meaning is actually some direction from a given point. So think always of these directions in which you want to go and search and so on. So what we did here was quite abstract. We just said we have a root finding problem, root findings, yeah. For convex problems we know this is equivalent to optimizing, but for non-convex ones we don't know actually. But if we translate it to a root finding problem, we can just say, let's solve this thing. This is not really as intuitive maybe as this method was before, where we just said, we somehow make a model of our objective function. Here we don't make a model of our objective function, we make a model of our gradient. And I just want to give a second interpretation to the Newton's method, which is actually based on a model. And the funny thing is we can actually say, let's look at this problem exactly. So I will give a second interpretation. Yeah? So for the same method. And this second interpretation is directly looking at this problem and saying, let's make some approximation which we can easier solve, and then if we solve this approximation, we get hopefully a better step. And this second interpretation uses actually a model. It's, so to say, a model interpretation, where we make a quadratic model of our objective. And this quadratic model we call M, and I call it MK. And it has one argument actually, and that is in the absolute values of coordinates, but I split this into xk plus p in order to keep a lot of minus signs away in the notation. And my quadratic model of my function at time point k is actually the function value itself plus the first order Taylor series term. And here I multiply it just with p. I could write this model differently, but then I would have more to write here. And then the last term that I add is actually the next term of the Taylor series, p transpose x, the second derivative of f. So this would be a quadratic model of my function based on a second order Taylor series. And now I could ask the question, let's minimize that. Yeah? So I could say actually that delta x at xk is given by the argument that minimizes p over all p, this model mk xk plus p. And now if you look at this model, you see already that there would be a serious problem if I would have a negative eigenvalue here, because then my minimization would be giving me an infinitely small value. But let's make the assumption that this Hessian is positive definite. So it's not only invertible, but it has only positive eigenvalues. And if I make that assumption, I could actually compute the minimizer of this model and guess what will be the minimizer of this quadratic function. We did that before. It will not depend on the function value. It will depend on the first derivative and on the second derivative. How do we get it? Actually, we would just set the gradient of this whole thing with respect to p to 0. Yeah? You look either bored or lost. Lost or bored? Lost. Okay, good. Thank you. So I need to be a bit clearer. I first write down what will be the result, and then I will actually derive it. So it turns out that this delta x is actually exactly the second derivative multiplied with f of xk, which is the same formula that we have above, right? So this step, and the interpretation that I want to give to this is actually the following. We have our nonlinear function. Okay, I might draw it somewhere else. So need not be convex, right? I'm at some point here. This is my x, and in this direction I have actually f of x. At a certain point, which is my current iterate, I take xk, and at this point I don't do just a first order Taylor series, but I do a second order Taylor series, and with a second order Taylor series I have something which depends on my coordinate x, on this thing, in a way that is of course tangential here, but it will be also having a quadratic component, so the quadratic model might look, for example, like this. Yeah, and this model is actually something I should draw in a different color. So I draw it in blue, and this would be the model at iteration k of x. Yeah, and this model, I think maybe you didn't like this notation. Was that the point that was disturbing you, or not? No, nothing. Okay, so this model is an approximation of my function f, which is actually absolutely exact at the point itself. So the values coincide, the derivatives also coincide up to second order. So it's in this case a very accurate model. And I minimized now this model in order to find that point. And this point will be then taken as xk plus 1. And in order to find now the optimal point of this model, I will just use the fact that my model is a quadratic function, and when I have a quadratic function and it is convex, because I assume this positive definiteness, then I can actually minimize, I could actually set, what I will do is actually mk, and I write it again with this form. Yeah? I can differentiate this whole thing with respect to p. And if I look at this thing, then I will get actually nabla f of xk transpose, okay, because by dp, then I will have a lying vector, so I could actually omit this transpose by making a transpose here, right? Then I have less transposes to write overall. And the second derivative, the first derivative of this term, which will be p transpose Hessian times p, second order term, will be, because of this 1/2, that will be cancelled, and the end will be the second derivative of fxk times p. And now this thing is what we have to set to 0, and then we invert that, and then we get that the p is equal to minus nabla square f of xk transpose nabla f of xk. Okay, so we got, actually we have just different paths to get to the same result, but I wanted to give you this interpretation. We call it the model interpretation because it's actually building a model of our nonlinear difficult function that we then can easier optimize, and then with this model we find a new candidate point which hopefully is better. Okay? And let me just say a few things. So for the Newton's method, we have the same formula, but when we just looked at this root finding problem, we did only make one assumption, namely that this matrix is invertible. For the model assumption, we needed to make even a stronger assumption, namely that this second derivative is positive definite, which is implying, of course, invertibility, right? So for the model assumption, we see directly that something would break down if our matrix would have negative eigenvalues. It would actually not have a minimum. This quadratic function would be unconstrained to the bottom, right? If you have a negative eigenvalue, you could just go in that direction, and this term will be dominating over everything else soon, at infinity. So, does it actually make sense to have a Newton method where this thing is invertible and not positive definite? Yeah? So what would happen, for example, if it would be negative definite? It would be invertible, right? So everything would be nice. But the interesting thing is that this Newton's interpretation, so the original one where we just want to find a zero of the gradient, this would work equally for a maximum as for a minimum, right? So it wouldn't make a distinction between maximizing and minimizing. Actually, if you want to minimize, making just sure that this holds could be very dangerous, because at the end your algorithm might just go to the next maximum, right? So Newton's method is extremely fast, extremely efficient. It will just go to the next root of the gradient. It might go up instead of down, so it's not such a nice thing. So instead we will usually go in this model interpretation, and whenever our second derivative does not satisfy this property, which we like, namely that it's positive definite, then we will somehow make sure that it satisfies this property, and we will modify it if necessary in order to make sure that we go down and not up. Yeah? So this is the thing that I want to share with you already here. I think in the script I don't want to go exactly the same way as I wrote it down some time ago. But I would rather like to ask, before I start the break, if you're familiar with local convergence rates. I mean, if you have iterates that converge to some point and you have measures of how fast they converge to these points, are you familiar with this notion of Q quadratic convergence or Q linear convergence or R linear? No, not so much, right? So then I think we will have a bit of discussion on local convergence rates already here, before we actually go on. And I think we do it after the break. So let's have a 10-minute break and continue 3:05. Okay? What we have looked at in the last hour was basically a variety of different algorithms that would produce a series of iterates in some space Rn that we hope do something nice, namely converge to a solution. And what we would like is that these things converge quickly to a solution, and there is a notion of convergence speed, local convergence speed, that I want to first define so that we can use language that is used everywhere in mathematics, but this language needs some definitions. And based on your feedback, I think I want to give these definitions. So it's about convergence rates. And maybe the picture, before we start to define them, the picture is that you are in some high-dimensional space Rn, right? So we are here in Rn. Here could be x1 and x, so the different components, but I will not give them the index because I need the index for the iterates itself. And then I will have some point which I call x star, and some iterates like x, here could be the point x0, here could be the point x1, and so on. And I'm interested in sequences that converge to this point. Yeah? So what I'm interested in, I want to look at sequences which have the property that as k goes to infinity, then I go to x star. And obviously this means that the norm, the distance between xk and x star will go to 0, right? So this is clearly just something like this. Xk minus x star will go to 0. So that's basically what we know already. That's the assumption. But now the question is, we want to say how fast does it go to 0? And there are different convergence rates, names for that. And these are the things that we assume, right? So we assume that it is already converging, but now we want to give a name to the speed of convergence. And I want to maybe start with the definitions and give examples afterwards, but there is one speed that is very commonly encountered in many of these optimization methods, which is called so Q-linear convergence. And what does it mean? It means that at some point when you have, that there exists an index here, and let me just define it. There exists some index k, 0, which is possibly big, so that for, and there exists also a number c, smaller than 1, so that for all k that are bigger than the k0, so all iterates which are big enough, far enough in the future, so to say, we have the inequality that the distance of the next iterate minus the distance to the true point, to the final point, is smaller than the distance that we had in the previous iterate, times a constant, and this constant is actually c, the linear contraction rate. Yeah? So c is the contraction rate. That would be the definition of Q-linear convergence, and another definition which is completely equivalent is actually saying that the limit of this divided by that, this divided by that this limit should be smaller than 1. So you could also have this definition that you take xk plus 1 minus x star divided by xk minus x star, and that this whole limit will be smaller than 1. Yeah. So this is Q-linear convergence, and why is it called Q-linear? Because Q stands, so to say, for quotient, due to this definition. Yeah? So because the quotient actually enters here. There is, you see that actually if you think of this, its linear contraction rate is something like radioactive decay, for example. If you have some radioactive substance and you wait one day, it will be reduced by maybe 5%, and then you wait another day, it will be reduced by 5%, and over the days it will converge to no radiation, but with a linear contraction rate, exponential decay actually. Yeah? So this is equivalent to, if you think of exponential decay. It's funny because it's not called exponential decay, it's called linear contraction, but it's the same. Yeah? So that's what you should have in mind. You can also think already that this linear contraction can be either very slow, so think of a substance like, I don't know, I think plutonium or something. It has a very slow decay rate, so one day to the next you will get maybe a reduction of 0.001%, and that means that for many, many years you will actually have to wait until it's converged to 0. If you take another substance which has a much higher decay rate per day, you will have to wait much less. So this contraction rate is of course crucial, and if you think of our numerical algorithms, these contraction rates, if they are smaller than, let's say, a half or a tenth or something, so then you really think there's substantial progress every iteration, and then you're happy. If you have a contraction rate which is close to 1, like 0.999% or some 0.999, it will give you very slow progress, and probably you don't like that algorithm. So Q-linear convergence can be in practice either bad or good, depending on how big this concept is, right? So when I say good linear convergence, what do I mean? This is not defined, of course, and good is very arbitrary, but then I will think something like C smaller than a half or something, right? So then I would say it's good because it's somehow contracting, it's making progress in some. Yeah, this is very approximate. But just to give you a feeling of what it would mean in practice. So now we go on with one contraction rate, which is also desirable and which many of our algorithms will have, which has actually a similarity to this Q-linear convergence rate, but which is called Q superlinear. Superlinear means it's actually better than linear, right, as the name says, and that is the next part of this definition. So what is Q superlinear? This is a bit easier actually to define. We don't need this K, but we just say there exists a sequence CK. Yeah? So it's a sequence CK, K starting at 1 going to infinity, which has also the property that the limit of CK is equal to 0 for K going to infinity, and we have the property that for all k, the norm of xk plus 1 minus x star is smaller or equal to, ck times the norm of xk minus x star. So what it is, it's actually linear convergence, but with the extra added benefit that this convergence rate, however big it might have started, will converge to 0, so that means that at the end, of course, these C's will be remaining positive, because otherwise this will be impossible to hold, right? But the CKs will eventually converge to very small values, and if you wait long enough, you will get good linear convergence. Or better and better and better, and that's why it's called superlinear. And so the main point is this thing, CK goes to 0. So the contraction rate gets better and better. Better and better. So that's what Q superlinear convergence does. And if you just reorder these expressions, you can again say the limit of this quotient xk plus 1 minus x star divided by xk minus x star for k going to infinity is actually converging to 0. So you really have this contraction to 0, not something smaller than 1, but to 0. These were the two which have linear in their name. And then there's something better, which Newton's method will have actually. And this better thing is a Q-quadratic. Better I say because it's actually typically faster in practice, but it's basically a different thing. Q-quadratic convergence, what is it? Q-quadratic convergence is that there exists, so what does it mean? There exists some constant C, it's actually a different constant with different units, so that we will have, and also there should exist a k0, otherwise this definition is not correct, so that for all k bigger than k0, we have the property that, and now comes the core point, that this distance to the optimal solution will shrink actually not with a linear rate, that's what we would have usually, or before, but we take actually a square here. And this square makes it different, and it means in particular if you make this, if this is already very small, the next time this part, so the distance will become even smaller. So my way to think of this is actually that your contraction rate itself, so I could actually maybe just give you this expression is actually C times xk minus x star. I make brackets around it and I multiply it with xk minus x star. This is just a very different, stupid different way to write it. But what you see is that actually this contraction rate, now I have a linear contraction with a rate which itself converges linearly to 0. Yeah? So this is one way to interpret it. Another way to state that actually by limit, and I think I should always have the lim sup here, right? I forgot that. I think I should have everywhere the lim sup. Sorry. And here I take this xk plus 1 minus x star, and I divide it actually by the difference x star squared, and even, yeah. So I divide it, so this should be smaller than infinity. So that's the condition. That is also equivalent to the statement that I had before. So I just divide this whole thing, and this constant c is not actually necessary that it's smaller than 1, like for linear convergence I needed that, but here, first of all, I assume that it's converging. That's already assumed anyway, but then at the very high rates when this is actually small, then this constant will eventually be smaller than 1 anyway, and then it will actually start to contract extremely fast. I think it's maybe nice to have some examples first, so that we can continue a bit with ideas. So I will actually regard extremely simple examples, so I will assume that these things are just real numbers, so then I don't have to worry too much, and I will assume that x star is equal to 0, then I don't have to subtract it all the time, and it will simplify my notation. But let us just think of some typical sequences that we could have. So these are examples. So one example sequence will be 1 over 2 to the k. Yeah, so 1 over 2 to the k, that's actually exponential decay. So we can directly see that's Q-linear convergence. And what will be its contraction rate? We can easily see. Actually, we can divide, if you want to say xk plus 1, you can divide by xk, and you will get, what will we get? 1/2. So we have a contraction rate 1/2, so it's at the border of being good, right? So we would say this is good. You could have also another thing. Xk could be 0.99 to the power of k. That's actually, so the contraction rate will be c. So it's actually also q linear, but the contraction rate will be exactly 0.99. So I wouldn't call that good. Yeah, so that would be very slow convergence. If you look at the numbers, how long they take until they come to 0, it will be very small. So this is A, this is B. Let's look at a third example, which would be xk being 1 over k factorial, just to give you some idea. So what will be the quotient of these two things, xk plus 1 divided by xk? It will be actually 1 over k plus 1, right? I think that's what it will be, right? And what you see is this converges to 0, so we have actually Q superlinear convergence. So you see already from the factorial, you know it grows very quickly, and that's actually why this xk will grow very quickly to 0. So something nice, right? And then there is an example which is difficult to write down, but this is actually what Newton's method will produce later on, but I just give you an indication, so how fast it is. Actually, we take 2 divided by not 2 to the k, but we take it by 2 to the 2 to the k. So this. This is nasty, isn't it? It's extremely quick. And that is where you would actually now, let's look at what would happen here. Xk plus 1 divided by xk squared, what will it be? Actually, it will be, let me just write it explicitly. So here we will have 2 to the 2 to the k plus 1. And then we divide it by this thing squared, but it will be actually the division of this is of course 2 to the 2 to the k and then squared, right? So what we will have is 1 over 2 to the 2 to the k plus 1, so that's the first part, and here we will get this 2 will be actually a sum, so this will be 2 times, right? So what we will get here is 2 to the 2k times itself, so we will get this thing times itself, which means actually 2 times. And that means actually that here we have 2 to the k plus 1, right? And that's the same thing that we have here, and that means we get 1, which is meaning that this quotient will actually converge. It's always the same, it's 1. So the nice thing about this thing, so it's Q quadratic. And what you see already from this example is that it converges very, very quickly to 0. And one way to think of what Newton's method or what quadratic convergence means is actually that if you would look at digits of numbers, so how fast something approaches the true value, the final value of the sequence is actually that the number of valid digits doubles in every iteration. So once you have like 2 valid digits, the next iteration you will have 4 valid digits, the next iteration you will have 8 valid digits, and then 16, 32, and your computer cannot be more accurate anyway. So roughly speaking, Q quadratic, and then in colloquial words, number of valid digits doubles in each iteration. For linear convergence, it's not doubling, but it's a slow progress. So when you have so to get 1 digit better accuracy, you have to wait the same number of iterations. Yeah?
So if the low digit is correct, then it doesn't converge?
No, that's of course, the funny thing is that's why what I said here already in the definition, right? At the beginning, when this thing would be too big, you would not have quadratic, you would not have from this inequality alone, you wouldn't have convergence. But we assume already at this moment that it is converging, and then if it does converge at some point, it will be small enough so that this actually will be smaller than 1, and then you get the effect of quadratic convergence. But what you say is actually extremely important, and we will see it actually this term. In some practical methods, you can actually make bounds, and they will lead to quadratic convergence bounds like this. And then the consequence directly is that you see, Newton's method will surely converge if this is close enough to the solution. But if it's not, it might not. And that's happening in practice. And that's why we need to think about things like how to find something that's close enough to a good solution. But thanks for this question. So there is actually another definition which is a bit weaker, which I want to give you just for completeness. And these are the R convergence rates. And historically, R comes from root. Yeah? And but I will not mention that. Actually, the main point here is that a sequence xk that converges to some point is R quadratically converging, or R, maybe I should keep it, is R converging with rate. And then you can have it either linear, or you can have it superlinear, or you can have it quadratically. Yeah. If there exists an upper bounding sequence for the distances, which is actually with a Q rate converging. So let me just explain it. So if there exists a sequence which I call now C, or should I call it differently? I call it Y, YK, that converges to 0, and which upper bounds these distances. So that xk minus x star is always smaller than yk. Yeah. So this is a real valued sequence where this yk has q quadratic or linear or superlinear convergence rate. So the point is, this is a weaker definition because we don't assume that this progress, this quotient holds in every iteration. And to just give you an example, I just want to give you one sequence which is actually, from each of these sequences I could make an R convergent sequence by just omitting every second member and replacing it by 0, right? So I could take, for example, this one, which I just take, it's 1 over 2k if k is even, and 0 if k is uneven. So you would just take different values, so it's a sequence which would be big, then it's 0, then it's big again, then it's 0, then it's, so it's going something, right? It's converging, and it's also converging practically as fast as actually a linearly converging sequence, but I cannot bound my distance at one point based on the distance that I had before. So it's a weaker condition. And the overview that I want to summarize actually, these convergence rates, how we could summarize them all, is actually that if you have a sequence that's converging q quadratically, that's the best thing that can happen in this universe that we define today. We have 6 rates. So if you have a q quadratically converging sequence, that will of course imply that it's also R quadratical, right? Quadratically. So this will imply that it's also an R quadratically convergent sequence. But it will of course also imply that it's a Q superlinearly converging sequence. Now that's clear from this definition. Here you see that the contracture rate is actually converging to 0. And of course Q superlinearly will also imply R superlinearly. And moreover, if you have something that's upper bounded quadratically, then you will also have something upper bounded that's superlinearly, so you also have this implication. So the queen of all these convergence rates is actually Q quadratically, and then it goes on with linear, because linear, Q linear is something you can have as well, and you can have R linear, that's what this example was, and that is also implied by Q linear. And among the things that we introduced until now, this is the weakest thing that you can imagine. There are weaker convergence rates, there are sublinear convergence rates, they are even slower, and some nasty algorithms will have this property. But here we are actually mostly interested in that. Newton's method has this wonderful property, and some of our algorithms will be linear. Okay, so I think this took some time, but it was good to do it. And what we will do next time is actually introduce a general convergence theorem for Newton-type methods in general, which will allow us to actually decide which of these contraction rates we will have, depending on the properties of our Newton steps. So let's continue next time. Thank you very much.